Okay, I want to talk about some of the efficiency metrics that we use for solid state lighting. And the basic thing that we want to talk about here are ways that we can compare lighting sources to things that we traditionally know. So for instance, one of the things, if you grew up in an era where you use incandescent bulbs, you oftentimes would see light bulbs sort of compared as 40 watt, 20 watt, 60 watt, 75 watt, and 100 watt light bulbs. And this really talked about the power that the light bulb consumed, but it really didn't tell you how much light was actually coming out of the bulb. And so somehow we have to come up with some sort of metric that we utilize to compare solid state lighting sources to these other metrics, or come up with a standard efficiency type metric that we can actually utilize to show that solid state lighting is actually more efficient than what you see with some of the other technologies. And so the first thing that we will do is use something called the internal quantum efficiency. And so again, this is a semiconductor device that we've said before that we're injecting holes and electrons into, and they are recombining and they're giving off photons. And so the internal quantum efficiency is talking about what is happening inside of the device, inside of these quantum wells that I've shown here with this process. So that's happening inside the semiconductor. It's basically the number of photons that are emitted from the active region per second, so it's a rate, divided by the number of electrons injected into the LED per second. And so basically, the rate of electrons being injected in, what's the rate of the photons coming out? If I have 100% of efficiency, for every photon that I inject, I get, for every electron that I inject, I get a photon out. And the way we calculate this is by looking at the optical power that's generated internally divided by the energy, which is Planck's constant multiplied by the frequency of the photons. And we're going to divide this by the current that we're placing across our diode, and dividing that by the elementary charge of an electron. And so that would give us basically the internal quantum efficiency of the LED. Now, the issue here is that all of the photons that are generated by the LED may not escape. So I may generate this photon here, it may get scattered around, it may not actually come out of the device. So we create something else called the extraction efficiency. So if I create a photon, I want that photon to come out of the device. So how efficient is this process? And so that is basically the number of photons emitted into free space. So this, I have the opportunity to actually see that photon, or for it to light up the room. So the number of photons emitted into free space divided by the number of photons that are emitted from the active region per second. And so the number of photons emitted from the active region per second, again, is based upon what's created from the recombination. And then we're saying that we'll actually, of those photons that are created, how many of them actually make it out into free space. So this is the total optical power that's generated divided by the energy, and this is the total optical power. This is the optical power that makes it outside of the device divided by the energy that's generated, and this gives us the extraction efficiency. And so now we talk about the external quantum efficiency, and this is the number of photons emitted into free space per second divided by the number of electrons injected into the LED. So before, we were saying extraction efficiency was how many photons do you generate and how many of actually make it outside. External quantum efficiency is the number of photons that are emitted into free space divided by the number of electrons that I actually inject into my LED. And this is simply multiplying the internal quantum efficiency, multiplying it by the extraction efficiency. Now, another efficiency metric, which may start to make maybe a little bit more intuitive sense to the layperson, is the wall plug efficiency. And basically, this is saying how much optical power do I get out divided by the amount of electrical power that I put in. So here's my P, which is the optical power, divided by the electrical power that I put in. So if it was 100% efficient, then all of the electrical energy I put in, or the power I put in, would be used to create photons. But as we know, most of our light sources get hot, so we know that there is some sort of inefficient process that occurs, that we will never have 100% efficiency in terms of the wall plug efficiency. But of course, you would want this to be as high as possible. And so what you'll see is that in some of the ways that we characterize the LEDs, the wall plug efficiency is definitely much higher than what you would find with, say, an incandescent bulb. And we're having higher efficiencies than what you would find with fluorescent lighting.